if we ignore the gravitational effects here, then I don't have to bring it in GH. Save that for later. So I know that the only forces acting on it, since I'm ignoring gravitational force, because I'm going to choose this is where x is equal to 0, that the only force really acting on it is that from the spring. And that's a conservative force. And just in case you're questioning it, because none of the springs you deal with are ideal, let's just go ahead and label them as ideal. So energy is conserved. I have kinetic plus potential equals kinetic final plus potential final. I'm about to ask that question, which all of you should know by heart. What's the formula for kinetic energy?
1/2 mv squared.
A single voice. That was that in sync. That was incredible. Sorry, it was not a chorus of angels though. And the initial squared plus, what's the potential energy formula for an ideal spring?
Is it 1/2 K? No, I don't think there's a half. It's K V squared.
K times what? It's 1/2 K. It is 1/2 K.
1/2 K V squared or X squared, whatever. It's displacement squared.
Since I'm letting x is equal to 0, that I can just get away with just an x there, which I'll do next iteration. What's K?
The spring coefficient.
Yes. All right, so I pull it down to there and I let go. Can I get rid of anything?
Well, the halves.
Oh, yeah, I can get rid of that.
Starting from rest, right?
Yes.
So the initial kinetic energy should be 0.
Okay, and that's pretty much it. We'll identify the other one in just a second. All right, so what we have here is, and we'll just label this as A. So I have K A squared is equal to MV final squared plus K, and I'm just going to say X final squared. This is some constant. The K is dependent upon the spring itself. It's a constant related to the physical nature of what we're working with here. Capital A is how far I pull it down and let go. So if I'm looking for my maximum speed, it has to occur when this is at a minimum. Because it's going to be a positive number. Any number that shows up here, that is going to take away from that. So therefore, it's going to happen when x is equal to 0. So I'm going to get maximum speed when I cross my threshold right here. And what I end up with is Vf squared, or I guess V max squared, is equal to K over M A squared. Let me just do the square root of that. So my V max is the square root of K over M times A. And what is the square root of K over M? You did that last week.
I have it written as omega.
It is, that's equal to omega times A. So using energy conservation, we have the maximum velocity, our maximum speed is A omega, and using the math, we get the exact same thing. Ooh. This is not one of those times I'm just gonna show that math was wrong. Now let's take a look at the acceleration. We have maximum acceleration right here, a omega squared. Well, if I pull this thing down and let go, the thing's gonna get pulled back. I know that the force from the spring is at a maximum when it's pulled down here. And again, ignoring the gravitational aspects of it. At that maximum location, I have, well, I'm at a maximum, so Ka is equal to Ma. So A is equal to K over M times A. Feel like if A is positive, if big A is positive, little a has got to be negative, so just so A is a positive number. And what's K over M?
Omega.
Square root of K over M is omega.
Omega squared.
So my maximum acceleration happens, ignoring that, at A omega squared. So we have found these values two different ways to get the exact same answer, which is helpful if you're panicking and can only think of one way of doing it. And we're about to do it another way. Well, we're going to do a more thorough derivation of the maximum speed happening at this point right here. Questions before I erase this?
Anyone want to just take a picture real quick? Thank you.
Nope, not that one. All right. So I have a spring that's kind of hanging out here. I put a mass on it and it's going to stretch some amount, just so that I use the same notation as I did here. Stretch down some distance y sub 0, and that's where I get my new mass. So this is equilibrium here. Since it's an equilibrium, I know the force down equals the force up, so I have mg down. I have k y naught acting up, and so k y naught is equal to mg. Then I'm just going to leave that right there. If you want to solve for k, we got that. That's what we want to solve for later. I now pull it down, and I let go. So not equilibrium. Now, obviously, from what I did in that second case right there, I am using the gravitational force here. I want to look at it from an energy point of view. Here we go again, in unison. What's the formula for kinetic energy?
1/2 mv squared.
Ah, that was much better. So 1/2 mv initial squared plus, well, I've got two different energies involved here, two different potential energies, two different conservative forces. What is the potential energy formula for gravitational force when little g is relatively constant?
MGH.
So that mgh initial. And for a spring,
1/2 k delta x squared. Or y squared. In this case.
makes sense to not use y over there. And then the same thing afterwards, 1/2 mv final squared plus mgh final plus 1/2 k delta y final squared. All right. Because the potential energy formulas have some constant that you can just always tack on, that gives us the freedom of picking 0 wherever we want. And so the question is, where should h be equal to 0? There are 3 logical locations.
At our point of equilibrium?
So right here? Okay. This gets stretched down some distance, y. And we will assume that that is a positive value when you stretch it. All right, can we get rid of anything in our equation?
Height initial is 0.
No. My initial is down here. What is the initial height?
Y delta?
Y, where's the delta coming from? You said Y delta, right?
Yeah.
Were you looking at this scribble right here?
Yes.
Oh, that's greater than 0, that just
Oh.
Y, just Y. Close.
Well, it'd be the same as, oh, never mind. I guess it wouldn't be the same as delta y.
No. Recognize that we have the planet down here. Deciding which is the positive or negative direction is fine when you're dealing with vectors, but I am pulling, as you get closer to the gravitational source, you're getting a smaller number. So it would be mg negative y. Plus 1/2 k. How much has the spring been stretched?
Y. Distance Y.
Yeah, it does look like a subvector every time I look at it. Spring has been stretched more than that. We're bringing, because we're dealing with gravitational forces in here too. Think about where the spring just naturally is and then how far we pull it.
Delta Y?
We can be more specific than that.
Is the y0 the distance from the relaxed spring and then the relaxed spring and the mass?
Yes.
So it'd be y0 plus y.
Yes. Equals, well, 1/2 mv v final squared plus, I'm just gonna drop that subscript since that's the only v we've got, plus mg h final plus 1/2 k. Well, let's see, we can simplify this some, because delta y is from the initial position. So it's y naught plus whatever y is. And hf is based upon 0 there, so this would just be negative y. I have to admit something up there, just a second. Negative y, and then y naught plus y squared. This is final. Now notice that over there on the first, on the initially, it's how far we stretch it down and let go. This, we actually do have a specific value for y here. It's however far we stretch it down. And we can even be so bold as to call that the amplitude. So that's the maximum it's going to stretch. I'm just going to label it as A just for the. So we got m negative mg a plus 1/2 k y naught plus a squared. But I've written all that stuff down, but recognize I have a specific mass, I'm at a specific planet, I have a specific spring, y sub naught is how far the thing stretched, which we can find from this equation right here, and a is just how far I pulled it down again. All of that is just some constant. I'm just going to label that a C0, because frankly, it doesn't matter what that constant is. And that's going to be equal to this at any point. So what I want to do is, if I want to find the maximum speed there, or the position of the maximum speed, well, I need to solve for v and take a derivative. And that's the fun of doing this, is the fact that we get to use a little bit more calculus. So I have some constant is equal to 1/2 mv squared plus, we can do a little bit better, minus mgy plus 1/2 k y naught plus y squared. Probably from a notational point of view, probably should put some I script I there. How do we solve for v?
Isolate the node.
Okay. What do you want to do first?
You can add mgy plus 1/2 k plus y naught plus y squared to the other side.
So bring it over?
Yes.
So I get C naught plus mgy minus 1/2 k y naught plus y squared is equal to 1/2 mv squared. All right, now what?
Multiply by 2.
So I have some new constant because I'm just taking the old one, multiplying it by 2. Plus 2mgy minus k y naught plus y squared is equal to mv squared.
Divide by m.
So I just have some new constant because I'm dividing by a constant. I assume the mass is not changing. Is equal to 2gy minus k over m. That showed up again. Y naught plus y squared is equal to v squared.
Square root.
I'm going to put it in exponential form. So some constant plus 2gy minus k over m y naught plus y squared to the 1/2. All right, so we have a formula here that's not worth memorizing because it's just from conservation of energy. But I want to find the position where the speed is at a maximum. So, since I'm trying to find the position where speed is at a maximum, take the derivative. And what is the derivative of v with respect to y? Oh, you're either skipping a step or you're doing it in a different order than I would do.
Probably a different order. Yeah.
Okay,
Or you
alright,
can do
so-
1/2, yeah, constant, some constant plus 2gy minus k over m y naught plus y squared to the, what is that, 3 over 2?
Derivative.
Negative 1/2.
Negative 1/2, all right.
And then 2g so that's minus km
If you need a tag team, you got two partners right there. I assume you worked on it.
is that just 2y? I think so.
I heard you say
2y.
2y.
So I wasn't, yeah, I thought there was something else, but.
All right, chain rule, you did the big thing first, so we got to the negative 1/2 and then negative 1/2 here. Now we're doing the inside, obviously, derivative of that, it's 0. That 2g, I'm fine with that. So now we get to this, well, that's just a constant. Take the derivative of the squared bit, so that's 2 times y naught plus y, do the first, and then the derivative of what's inside here, which is,
Just why not?
it's a constant.